Hey, flipped chemistry, how you doing? You ready for another lecture? I am. Let's get into it. You have recently been working on your own with some note gathering activities to teach you how to calculate oxidation numbers. I am going to just reinforce that real quickly, but you've done most of the work on your own, and then we're going to jump into how to name molecules. Okay, so here we are talking about naming molecules and just a quick recap of oxidation. Oxidation states that is the number of electrons that an element needs to get to return to a natural state. So if an element has lost electrons, it needs them back in order to get to a natural state, so its oxidation number will be positive. If an element has gained electrons, then it needs to get a negative number of them to return to a natural state, so its oxidation number will be negative. Basically what that means is that the oxidation number is almost always the same as the ionic state. Calculating oxidation numbers is usually as simple as looking at what the ionic charge is. So in an ionic molecule, you can see, oh, you're a charge of 3, your oxidation number is 3. You're a charge of -1, your oxidation number is -1. Even in covalently bonded molecules, you can look at what that atom normally does when it becomes an ion and get its oxidation number. So everything in the halides row becomes a -1 ion when it ionizes. So even in a covalent bond, its oxidation state is -1. Everything in the alkali metals becomes a +1 ion when it ionizes, and its oxidation state in a covalently bonded molecule is +1. There are a whole list of rules that you covered last week, and if you want to see the rules again, pages 190 and 191 will illuminate that for you. But for right now, we're just going to go on past this concept. We will use it a lot in the future, but I just want to remind you that you've run across oxidation numbers, okay? So let's get into naming compounds. A well-created name tells you everything you need to know about the molecule in order to draw its structure or draw its Lewis structure. And so naming is very important, and this is scriptural as well, right? Names are very important in the Bible. When people are named by God, or even when they're named by their parents, the name is not just something to call that person. It bears out some aspect of their character. And so naming molecules, while not spirit-led, is in fact the same kind of idea. The name tells you something about its character. And so when we name a binary covalent molecule, by that I mean a covalently bonded molecule that has 2 kinds of atoms in it, then we will use Greek numerical prefixes, mono, bi, di, tri, etc., to indicate the number of that kind of atom. And we will name the least electronegative atom before the more electronegative atom. And then we will stick "ide" at the end to try to let you know that it's a binary molecule. The Greek prefixes tell us that it's covalent. You'll see in a minute that "ide" is also used of ionics, but the Greek prefixes are only used of the covalent molecules. If that winds up creating a double vowel, then we truncate it. We remove that double vowel, so it's easier to say. So let's go through some examples. Water, we call it water, but the fancier name for water, the more chemically appropriate name, would be dihydrogen monoxide. Dihydrogen, 2 hydrogens. Monoxide, remember mono is 1. Monooxygen is 2 O's there, so we took out one of them, so just say monoxide. And then the ide is that this is a binary molecule, okay? Dihydrogen monoxide. You're used to calling this molecule carbon dioxide, okay? The carbon, we don't have to say mono before the first item if there's only one of them. We do say mono around the second item, but for some reason they don't necessitate that you say monocarbon dioxide. If the leading element is only one, we just say its elemental name, okay? Carbon dioxide. Binary ionics, very similar. We still say "ide," we still name the metal first, and then we truncate the second one and stick "ide" on as the suffix, but we don't use Greek prefixes. So this is not monosodium monochloride. This is just sodium chloride, right? Sodium chlorine, sodium chloride. This one, what would this be? It's potassium and iodine. Potassium iodide, right? So we just stick "ide" at the end, and we kind of truncate the last word so that it doesn't become iodinide. We just take off like the last syllable of the second element name and replace it with "ide." So sodium chloride, potassium iodide. Polyatomics are a lot harder, and you need to basically memorize them. And there's a table in your book that we'll go over in class. And this is one of those times when it's just gross rote memorization and you have to do it. So Merry Christmas, memorize. But the logic behind it is that we name oxygen-bearing polyatomics, which almost all of them are oxygen-bearing. We name them on their relative amounts of oxygen. And not even that really helps. So the examples here are ClO4, ClO3, ClO2, and ClO. Those are all polyatomic ions, and they all have chlorine in them. So it's chlor in all of them, right? Chlor is the central atom, the least electronegative atom, okay? And then it can have 4 oxygens, 3 oxygens, 2 oxygens, or 1 oxygen. Generally speaking, if something has only 2 possibilities, which most of them do, then we'll have an ate and an ite. Ate means more oxygen. Ite means less oxygen. So sulfate, sulfite, SO4, SO3. Okay, and various other examples of ates and ites. Ate has more oxygen than ite, but it doesn't necessarily mean 4 oxygens and 3 oxygens. It might be 3 oxygens and 2 oxygens, like nitrate and nitrite. Nitrate is NO3, nitrite is NO2. So it doesn't tell you distinctly how many oxygens. It just says this is the one with more, this is the one with less. And then if something has more than 2 options, if it has 3 options or 4 options, like the chlorine-based polyatomics, then what we wind up doing is we wind up sticking per as a prefix in front of the word and still using ate for the most oxygen, and then hypo as the prefix and still using ite as the suffix for the least oxygen. So perchlorate is ClO4, chlorate is ClO3, chlorite is ClO2, and hypochlorite is ClO. Again, that helps a little bit, but basically you just need to memorize these things, okay? So have a good time with that. Multiple oxidation states. Sometimes you have to identify the oxidation state of an atom in a molecule before you can name that molecule. This usually happens with transition elements, the elements down in the D block of the periodic table, and also the F block. And so these 2 parts of the periodic table, the atoms can be satisfied with different numbers of valence electrons, and so it will form double bonds or triple bonds or single bonds and share different numbers of atoms depending on the situation, different numbers of electrons depending on the bonding situation. So you have to indicate what the oxidation state of that atom is in molecule before you can name the molecule. And when you do that, you use a Roman numeral after the name of the atom to indicate its oxidation state. So an example would be iron 2 oxide, which is FeO. Iron can also have a 3 oxidation state, and we recently in a lab used a substance called iron chloride, FeCl3. In that particular situation, the iron has taken on a +3 oxidation state, so that would be iron 3 chloride. Here we have iron 2 oxide. Okay, and you can have iron 3 oxide as well, Fe2O3, and so that's another option. So you have to identify the oxidation state. Tin is another one of those transition elements. So tin 4 oxide is SnO2. So the 4 is not how many tin atoms there are. See, there's only 1 tin atom, but it's the oxidation state of that tin atom. Alrighty. Lastly, hydrates. When we name compounds, sometimes the compound doesn't come just by itself, but it brings along some water molecules as friends. So here we have an example where something is is itself. It's in this crystalline state, and then it has water molecules traveling with it, surrounding it, and in this sort of like ice matrix. And but it's not cold like ice. It's just water molecules attracted in a very strong way to the central molecule that we're naming. So we have to name the molecule that all the water molecules are stuck to, and then we have to say, and water's along for the ride. We call that a hydrate. And so we'll use the Greek numerical prefixes before the word hydrate to represent how many molecules of water travel with every one molecule of this thing. If there are no water molecules, but there could be, then we call it an anhydrate. We say, hey, normally this molecule travels with water. In this particular example, it's not, so this is something anhydrate. But if it travels with one molecule, which is very rare, it would be monohydrate, dihydrate, trihydrate. Usually you wind up with like pentahydrate, hexahydrate, nonahydrate, because water molecules will be globbed all over the thing that we're caring about. And so you name the central atom, then you name what's surrounding it. Let me show you a picture. This is an example of methane hydrates. So they just drew a green circle, but this is in fact a gas molecule, methane. And then it's surrounded by tons of water molecules that are frozen into a lattice. And this looks like ice and snow. It's really cool. I'm going to show you a video in class of burning snow. Blows your brain. But we have ice surrounding gas molecules. And this would be an example of a hydrate. Okay? If you have any questions, let me know. I will see you tomorrow. Jesus loves you, and so do I.